Greetings, physics family. We are doing our free body diagram quiz review, which means if you look at the very top, we've covered net force, which relates to free body diagrams, but also relates to Newton's second law, F equals ma. Don't forget that the force of gravity is the same as weight, and we can find weight by taking mass times the acceleration of gravity. We've talked about friction. We know that friction is equal to the coefficient of friction times the normal force on those objects, and that the overall net force we figure out by just adding up all the forces in either the x or y direction. So let's take a look at our quiz review, starting with number 1. Why can an object move at constant velocity if all forces acting on it are in equilibrium? Let's think about that. Say we have the force of gravity and normal force acting on an object. Totally possible. Say that we have an applied force pushing to the right, and with the same amount of force, the force of friction pulling back. All of these forces can be in equilibrium. So a lot of people think, well, if everything cancels out, shouldn't you be not moving? But that's not true. There's no net force, so we know there would be no acceleration if there's no net force. However, you can still be moving in constant velocity because inertia. If the object was already moving and then the applied force simply cancels out the force of friction, you can move at a constant velocity. Remember, inertia, an object in motion wants to stay in motion. Therefore, an object that's already moving wants to continue moving straight and at a constant velocity. So it all has to do with inertia. Let's look at number 2. What are the units that make up the Newton? Well, if you think about it, force is what we measure in newtons. And if you think about it, let's think about F equals ma. So we know that force is in newtons, but mass we measure in kilograms, and acceleration we measure in meters per second squared. So by looking at the formula, we actually figure out what units make up a newton. A newton is a kilogram meter per second squared. Simple as that. Taking a look at number 3, when pushing a box across the floor, it is more difficult to get the box moving than to keep it moving. Use inertia and friction to explain why this is true. All right, no problem. First of all, let's think about what's going on here. To get the box to move, we have to overcome static friction, right? And to do that, since the box isn't moving, we also have to overcome inertia. So overcome is an important word to use here because we have to overcome inertia and friction in order to get this thing moving. Now, excuse me, it is difficult to overcome inertia and friction, but once you get it moving, an object in motion stays in motion, so it becomes easier to move the object. So once it's moving, we're good. It's not as hard to continue pushing that object. So inertia and friction have tons to do with that. Remember, whenever we do the force equation, right, static friction versus kinetic, static is always that highest part of the graph where kinetic is less force needed. So static friction is always greater than kinetic friction, and it has to do with the fact that you have to overcome inertia when an object isn't moving. Taking a look at number 4. It says a 25 kilogram penguin. All right, so first of all, let me start organizing my information. I don't know if I'll need it all, but I'll organize. 25 kilogram penguin slips on a wet rock. I love penguins, by the way. The coefficient of friction between the penguin and the rock is 0.35. So the coefficient of friction is mu, 0.350, and there's no units for the coefficient of friction. We want to know what the frictional force is that impedes the penguin's motion. All right, so we're looking for the frictional force. So I've got my givens and my unknowns. All right, G and U. Perfect. Now, what equation am I going to use? Well, in order to solve for force of friction, I'm definitely going to want to use the force of friction equals mu, or the coefficient of friction, times normal force. Yikes, but here's the problem. I don't have normal force. I was given mass. So is there a way to figure that out? Yes, I'm also going to need to use the equation weight is equal to mass times the acceleration of gravity. Now that I have that, I can solve for weight and assume that that's equal to the normal force. Here, let me solve for weight, and then I'll show you what I mean, how weight and normal force are equal. So the weight of this object is going to be the 25 kilograms times negative 9.8, which is the acceleration of gravity. I multiply those two numbers together, and I end up getting about 245 newtons. Now remember, if this penguin has a force of gravity down, then we can assume that the normal force pushing up on the penguin is equal. So if downwards this is 245 newtons down, we can assume that the normal force pushing up is 245 newtons, which is great because we need that normal force to plug into this equation. Now that we have that number, we can finally plug into our original equation, force of friction. So my force of friction is going to be equal to mu times the normal force. Remember, mu is the coefficient of friction. So force of friction, I don't know, I'm going to solve for. Mu is 0.35, and normal force, we figured out, was 245. Multiply those together, 0.35 times 245, and we end up getting about 85.75, and since this is a force, it's going to be in newtons for our answer. So there you go. It was like two problems in one. We had to first convert our mass into weight because we know that the weight would be equal to the normal force. So we're manipulating data to make it work for us. Taking a look at number 5, it says fill in the blanks for an object being pushed across the floor to the right with 30 newtons of applied force. Okay, so this is my applied force. So I'm guessing that this is my force of friction. If I'm pushing something across the floor, gravity's got to be pulling down, and this must be my normal force pushing up. Now I want to try to figure out everything I can about this information. So let me see. To get mass, I know that mass is the same as, not the same as, but mass can be solved in the weight equation, and I know that weight and force of gravity are equal. So I'm going to take my weight equation, which I know is 25 newtons. I don't know my mass, but I know gravity's acceleration is negative 9.8. Now that I have that, I can divide negative 9.8 to both sides. And when I do that, my mass ends up being 25 divided by negative 9.8. And I think to myself, wait a minute, this is going to be a negative mass? That can't be possible. But don't forget, 25 newtons is a downward force for the weight, so I can put that as negative. Now my mass won't be a negative value. I end up getting about 2.55 kilograms, which is great. That makes more sense. I don't want a negative mass. Mass is a scalar quantity. It doesn't have direction. All right. So let's see. I got mass. Check. Acceleration. Yikes. I can get acceleration through F equals ma. But I know the mass, but I don't know my acceleration yet. So, and I don't know my net force yet. So I don't think I can solve for acceleration. I might have to come back to that. How about net force in the x direction? Okay, net force in the x direction is the horizontal. All right, I can figure that out. Let me do that down here. Net force in the x direction, so I use sigma F, is going to be the applied force forward plus the force of friction, which is backwards. So if I want to find my net force, we're just adding up all the forces in the horizontal direction. So force applied is 30 newtons, and force of friction is 15 newtons, but remember it's backwards, so it's going to be a negative. So when I add those up, 30 plus a negative 15, I end up with a positive 15 newtons overall for my net force, which means that my net force in the x direction is 15 newtons forward. So I might put a little plus sign to remind myself. You could say to the right or forward, or just leave it literally as 15 newtons because it's positive, that's the direction. But now we found our net force. Now that I have that, can I circle back to solving for my acceleration? And the answer is yes. My net force is 15. My mass, I figured out, is 2.55. Let me solve for acceleration just by dividing by 2.55 to both sides. Cross that out. Acceleration is going to be 15 divided by 2.55. And what I end up getting for an answer is about 5.88. So I'm going to put that in my acceleration, 5.88, and don't forget my units, meters per second squared. Awesome. Now that I have that, yikes, I want to find mu. Okay, well, mu is only found in my equation for the force of friction. So let me clean up a spot and let's see if we can tackle that one. All right, perfect. I know that my force of friction equation is going to be equal to mu times my normal force. So can I plug in to eventually solve for mu? I'm confident I can figure out that information. So what to do first? Okay, well, I've got my force of friction, which is 15 newtons, so I'm going to plug that in there. I'm solving for mu, the coefficient, so I'm going to put that there. What about my normal force? Oh, it's right here in my free body diagram. So that's 25. Okay, so getting the coefficient by itself, mu, looks like I'm going to divide both sides by 25, and I'm going to end up doing 15 divided by 25. When I divide those, I think I end up with, let's see in my calculator, 0.6 for my coefficient. Remember, my coefficient doesn't have any units, so it's just going to be 0.6. But look at that. All that information I pulled off of this free body diagram. Pretty impressive. And just to recap, we used a couple different equations. The weight equals mass times gravity, Newton's second law, force equals mass times acceleration, and the force of friction equals mu times the normal force. Nice job. Page 1 done. Let's tackle the back. Checking out question number 6. I have a 55 Newton force is applied to drag a 30 kilogram box across sand with an acceleration of 1.55 meters per second squared. Diagram the forces acting upon the sled. Wow. Okay, let's see. They gave me mass, so that might be important later. They gave me acceleration, so let's see. I'm dragging it across the sand, so that must be acceleration in the x, the horizontal direction. Since I'm dragging it across the sand, I'm doubting nothing is happening up and down with acceleration. So I'm going to assume that there's no acceleration up and down, which means there's no net force overall up and down. All right, let's see what I can do here. I've got a sled, it's 30 kilograms, so I'm going to put the 30 in there. Obviously, there has to be a force of gravity, and if it's on the ground, equally pushing up is going to be the normal force. All right, I have a force applied, so I'm going to have that applied force pushing forward, and it's going to be 55 newtons. Perfect. And since I'm dragging across sand, I can assume there must be a force of friction pulling back. I don't know how much, but I'll figure that out. All right, looks like I've got plenty of information. Let me start plugging up some of these holes. First, if I want to find the overall net force, I know that my net force in the x direction, that's the horizontal, is going to be I can't do applied force plus force of friction because I don't really know force of friction yet. So maybe that's not going to work. But there's another way I can find net force. It's F equals ma. And I have those. I know the mass is 30. My acceleration given to me is 1.55. So if I multiply 30 times 1.55, I end up with about 46.5 newtons. All right, figured that out. Awesome. Now, because I know the net force in the x direction, I can figure out what my force of friction would be. Why? Well, remember, if I take the net force in the horizontal x direction, it's really just the applied force plus my force of friction. So I know my overall net force is going to be 46.5. My applied force is already 55. So what on earth must be my force of friction? Easy. I'm just going to subtract 55 from both sides, and I'll solve for my force of friction. So 46.5 minus 55 ends up being about negative 8.5. So it looks like my force of friction is negative 8.5 newtons. All right, so I've got my force of friction, my applied force. I need to find my force of gravity and my normal force, and eventually mu, my coefficient. But remember, for my coefficient, I'm going to need normal force in my equation. So it looks like I'm going to have to solve that next. No problem. I know that my force of gravity is the same as weight. And I know that weight is equal to mass times gravity's acceleration. So my weight, or force of gravity, is going to be equal to the mass, which is 30, times gravity's acceleration, which is negative 9.8. 30 times negative 9.8 gives me about 294 newtons, I'm thinking. All right, so that looks like 294 newtons downward. I'm going to put a negative. And then that means the normal force up is about 294 newtons upwards. Remember, the force of gravity down, if an object's on the ground, the force of the ground pushes back up with the normal or support force that is equal to it. So it looks like 294 up and down, and that makes sense, right? Because up and down forces that are the same mean that in the y direction, the net force is 0. All right, so the only thing left I have to do is solve for my mu. Man, I better make some room here. So let me erase and then get the place set up for my force of friction equation. If I'm going to solve for mu, then I know I have to use my force of friction is equal to mu times my normal force. Perfect. Let's plug in. My force of friction I already figured out from my free body diagram. It's 8.5. Mu, I don't know, I'm solving for it, but my normal force up here is 294. Perfect. Let me divide, whoa, that wouldn't work. Why would I divide by 8.5? See, that's good. I'm paying attention, catching my mistakes. I'm going to divide 294 to both sides to get mu all by itself. And when I do that, 8.5 divided by 294, I end up getting about 0.03 for my answer. So solving for mu, pow, is right there. Wow, take a look at that though. All that information, we just had mass, applied force, and acceleration, and we figured out all these other things. That's a jumbled of a mess, but hopefully you followed along one step at a time. Don't let all the little side work overwhelm you, because it is a lot of writing. But in the end, you grabbed a lot of information from a little bit of initial information. That's impressive. And let's look at question number 7. You've got a 2.5 kilogram flying squirrel is flying from a tree to the ground at constant velocity. Whoa, whoa. Constant velocity is important because that is going to tell us something. Constant velocity automatically tells us that there's no acceleration in any direction. So meters per second squared is right there, 0. Also, don't forget that if there's no acceleration, there's no net force either. So that means that all forces are in equilibrium. It says, consider air resistance, diagram the forces. So if this squirrel is falling, we know the force of gravity is pulling on it, and equally an upwards force of air resistance is on it. So that was a pretty quick question. The only thing we need to do now is figure out what the forces are up and down. Don't forget, if these forces up and down are equal, once we figure out the force of gravity, we can figure out that it's the same or equal to the force of air resistance. So don't forget, force of gravity is the same as weight. We know weight is mass times gravity. So my weight is going to be the mass, which is 2.5 for the squirrel, times negative 9.8. If I throw that in my calculator, 2.5 times negative 9.8 is 24.5. So that means the force of gravity downwards is 24.5 newtons. Technically, this weight over here would have been negative because of my negative 9.8 acceleration. So that means my air resistance, since these are equaling out each other in equilibrium, is an upward force of 24.5 newtons. All right, constant velocity sets it crazy. Everything ends up equaling zero because Newton's second law states if you have net force, you have acceleration. So if no acceleration, no net force. Looking at one of our last final questions, what is the meaning of all of these terms? So first of all, sigma F with a Y just means net force in the Y direction. Remember, think of it like a graph. The y-axis is up and down, x-axis is left and right. So this is the net force in the y direction. Feel free to write that down. For B, this is the net overall force in the x direction. So any forces on the horizontal axis added up is going to be your net force. FBD stands for free body diagram. Free body diagrams are the things that we've been drawing with all the forces. Terminal velocity. Remember, terminal velocity means that an object is falling at a constant velocity. And at terminal velocity, when you're falling, it means the force of gravity and air resistance are equal to each other. Why? Because they have to cancel out the net force so that you can accelerate. So air resistance is equal to your force of gravity. That's why you don't speed up. Inertia. Think about inertia. We know that mass affects inertia. The more mass, the more inertia. In fact, we measure inertia by mass. But what is inertia? Inertia is the object's resistance to a change in motion. What the heck does that mean? It simply means that if an object is resting, it wants to continue resting. And if an object's moving, it wants to continue moving at a constant rate or constant velocity at a constant direction. Think about that. Mass, we know, is the amount of matter, and mass ties into a couple things, right? Mass is definitely related to the weight equation, and also our net force equals mass times acceleration. So it's part of the second law for Newton. Also, don't forget that if mass increases, acceleration of the object will decrease, and vice versa. If mass decreases, acceleration will increase. If you cut mass in half, you will double acceleration. If you double the mass of an object, you will cut its acceleration in half. They're inversely related. What is weight? We know that weight is also just the force of gravity, and that weight is the force from gravity having us push down on the ground. Acceleration is if an object is speeding up or slowing down. And we know that acceleration is strongly related to the net force. Whatever direction the net force is in, for example, if it's forward, acceleration will be in the same direction. That's part of Newton's second law. You have to have an unbalanced force to have acceleration, which means you have to have a net force. Mu, this symbol right here is the coefficient of friction. What on earth does that mean? That's a number given to an object depending on what it's touching and its value for friction. So if it's more rough, the coefficient will be larger. If the object is more smooth and slippery, the coefficient value will be smaller. Static and kinetic friction. All right. Static means that the objects are touching but not moving, or kinetic friction means that the objects are touching and moving past each other. Remember, in a force graph that looks like this, static is always the larger amount of force because it's harder to overcome inertia to get the object to move. And we know that static friction is when the object is not moving. Then once you get it moving, kinetic friction kicks in, and it's always a little bit less in the area of force. Equilibrium is an important concept. Equilibrium means that forces are canceling out. So for example, on this one, air resistance and force of gravity are equal top and bottom, so they cancel out. So these forces are in equilibrium. If your forces are completely, all of them in equilibrium, then you have no net force. And speaking of net force, up next, net force we know is either written as sigma F or F net, but we know that that is always equal to mass times acceleration. Net force is your forces added up either in the y direction, up and down, or the x direction. For example, if we go back to this free body diagram right here, the net force in the x direction would be nothing because there's nothing horizontally. But the net force in the y direction would be the air resistance force plus the force of gravity. So remember, the total net force is the forces added up in the y or x direction. Also, don't forget that we can find net force, of course, from F equals ma. Both are important to understand. What is normal force? Remember, normal force is not the same as net force. Normal force is Fn. And when you have an object on a, let's say, some type of structure like the ground, we know force of gravity pulls down on that object, but the ground pushes back up with the support or normal force. So your normal force is just that upward force. A lot of times, if the object is just sitting on the surface, the normal force and the weight of the object or force of gravity are equal. And terminal velocity is mentioned once again. We already talked about it up there, so we're over that already. Nice. Good job, and hopefully these symbols and ideas are meaning more and more. Remember, physics isn't only about the equations and solving for numbers. It's understanding the concepts and how they all relate to each other as well. And lastly, what are the points of Newton's second law? Remember, in order to accelerate, you have to have net force. That's the idea. And remember, whatever direction net force is in, so say it's up, acceleration will always be in the same direction. If net force ends up being to the left, acceleration will also be to the left. So whatever unequal, out of balance forces there are, that's where the net force goes, and the net force tells you the direction of acceleration. You have to have an unbalanced net force in order to accelerate. And Newton's second law talks about that. The idea that F equals ma. The idea that our net force is going to affect our acceleration. Now remember, mass and acceleration are opposite of each other, or inverse, but net force and acceleration are directly related. So if net force goes up, so does acceleration. If your net force decreases, that object isn't going to accelerate as much. So there's a direct relationship there. All right, I think we've talked enough about Newton's second law for now. Nice job with the quiz review. Hopefully these things are making more and more sense. And of course, the quiz's idea is to figure out exactly what we do and don't know. We learn from our mistakes, capitalize on them, learn them, do better on the next quiz, and eventually the test to prove exactly what we know. Keep hanging in there, physics fam. You're doing great. Be well.